Hi, this is Mingyao from Ozen Engineering, and in this video I'll be looking at how to set up a refrigerated container simulation in Ansys Icepak. Icepak is a great tool for modeling thermal analysis. It combines computational fluid dynamics as well as the heat transfer, turbulence, and even mixture and humidity and things like that. So it's pretty good for modeling a refrigerator truck. It can be used to simulate small devices on the scale of a single computer chip or entire data centers. So we're somewhere in the middle here. We always start with this cabinet, or in this case, the container in the model. And we're going to use this as our initial analysis. What I often do is, in this case, the units will be changed to imperial units. So we're going to be using feet. And that makes setting this up a little bit easier. So on the X side, I'll set this up to 20 feet. Y is 8 feet, and Z is 8.6 feet. Yeah. So now our cabinet is reflective of our container. We want to go to the cabinet and change the wall type. So they're all going to become walls on each side. You can adjust the background of Icepak, and usually a dark background works better because most of the colors are fairly light. Okay. So I have all 6 sides to my cabinet, and we can put in some material properties for that. Okay, so I'm going to go. I selected all of the sides to this. I'm going to edit the properties. And this will be, we can specify a wall thickness, but let's change this to maybe 6 inches. And the solid material will be let's see, a polystyrene foam. This is a basic model. Let's edit this again. Let's make this effective thickness. So this means that we're not physically modeling the property of that. So that was the minus X. Just making sure. Looks like we have to manually adjust each one of these then. 6 inches. Oh, this external material, this is for radiation. We want to polystyrene. Oh, effective thickness. Should be able to edit all of these at the same time. Okay, so now it's editing multiple of them. So let's, that will save me some work. 6-inch effective thickness. Okay. Now I want to select all of them. And the other part is that we want to specify heat transfer coefficient. So right now we're modeling as if this is exposed to ambient air. The bottom shouldn't really have any heat loss, so maybe I should not select the minimum Y. We'll assume that's insulated. So I will select these 5 sides, and I'll say this is this will have a heat transfer coefficient of 5 watts per Kelvin per meter squared. Okay, so that's the outside. We're going to model this as if we're trying to keep something cool in a warm place. So going to basic parameters, defaults, we're going to set this to, let's say, 110 degrees Fahrenheit. So it's going to be a hot day outside. That's the ambient temperature that we will have in the system. And then we can set up some HVAC system, maybe some payload. So let's start with the payload. We have a block here. We can set it to, I don't know, let's say suggest a Y first. So maybe we'll have this on the bottom sitting in the trailer and model this as if it's fairly well loaded. So X will start here and end somewhere back here, and then the Z axis will be kind of okay. Let's set up the material property for this block. I'm going to make it water, so it's but it's going to be solid water. So let's get the material properties. Water is a liquid, so we first select the water material, and you can see it prints out our specific heat, density, conductivity. So then we're going to make a new material using this button here. This new material, I'll call it water solid. And it's going to be a solid material. Density will be 1,000 kilograms per meter cube. Specific heat. We can choose to make this linear or temperature dependent. In this case, I'm going to just make it a constant value. So this is joules per SI unit is 4180, and conductivity will be 0.6. Okay. One thing that's helpful to point out is that right now I just made the walls of this trailer polystyrene, but we can also make it a composite material. We can change any of these values from isotropic to orthotropic, anisotropic, biaxial, or scylla-orthotropic. So you can see that conductivity type can easily be made into orthotropic, and we can specify different type of material as needed. But for now, let's just go ahead and make this out of my water solid material. Okay, and it reflects back on the material properties I put in. It all looks the same, so I think we're good to go. So I have a big block of material in there, and now I'm going to put in an HVAC system. So this is cooling. We probably want to put the cooling on top, let it drop down, and then we suck it back out somewhere. So let's put in a opening. One of the nice things about opening in Icepak is we can make this a recirculation opening, which means whatever we extract a certain amount of energy from the system during the simulation process. I'm going to make this XZ because we want to put this on the ceiling, and let's go ahead and put it on the ceiling here, right in the center. Maybe we want to move it more to the back here. So we're going to move this in the x-axis, maybe to back here. Maybe we'll make this 3 foot long, something like that. Then that's a supply, so that's where the cold air will come in. I'm going to switch this to the extract, and I'll put this on the bottom somewhere down, maybe over here, to suck away the cold air. Or maybe it should be on the bottom of the maybe it should be on the wall. We can play with different locations, but let's put it on this wall for now, and move it a little bit over here, and maybe a bit lower. So we start down here somewhere and end up somewhere here. Okay. So we can specify a temperature change or heat input or extracted. We can specify a volumetric flow rate in cubic feet per minute. Okay, I'm going to make up some values here. I'll just put 1,000 cubic feet per minute of flow rate, and we can extract energy from this. So let's do watts, maybe minus 10,000 watts. We're going to try to keep this thing cool, and we'll see what temperature it ends at. So that's all there is to a basic analysis. We can also import geometry and have more detailed models of what's inside, but here is going to give us a simplified view of maybe depending on how full this truck is, what the temperature will be. Gonna go through the automatic setup wizard. So we're gonna have velocity, pressure, and temperature. We can add a humidity later on if needed. We're gonna have, this will be a buoyancy driven flow, just so we can specify gravity minus y-axis. That also looks just fine. We'll set this as turbulent flow with standard K epsilon. We can include heat transfer. We probably don't need it for this case, but we can use a discrete ordnance model here. Standard radiation modeling is included in Icepak. We want to include a solar radiation model, so we can specify the solar flux direction or have a calculator. So maybe we want this to be in June at noon here. Okay, so we want it to be maybe, let's do July 1st, maybe at 3 in the afternoon, so that'll be 1500. And latitude, we're gonna do 37.38 and minus 121.99. So this is the Sunnyvale location. And we'll do -7 to correct for Pacific time. And that's going to put in the solar radiation here. We're going to start with a steady state simulation, and that's it. So we're ready to go ahead and do the analysis. Typically, let's run a couple hundred iterations. Parallel setting, we typically run, I'm running this on a simple laptop, so I'm going to use 5 cores, and typically it's a good policy to monitor some locations. So we can create monitor surface here, and we're gonna monitor the temperature of this opening tube. We can select this is the opening, and I think that's good. We should probably also monitor. Let's try to monitor the temperature of this block too. And we can just do a monitor point right in the middle of the block. And now we're monitoring the point of the block. So that's ready for simulation. We can go through the process of, let's generate a mesh here. The model is super simple, so the mesh is extremely small. We can take a look at the mesh here. It's a fully structured hex mesh that represents the size of the geometry. So I'm going to go ahead and run the simulation. We can make it a bit more refined later on if needed. Oh, doesn't like the minus value for my longitude. So we can step through this here, and I think we can just change this to positive. It's north and west. There you go. Okay. Let's try that to run this again. We can enable pressure velocity coupled formulation. This sometimes goes a little bit faster. There's an option to use the pseudo transient, or we can just let this run by default. Now it looks like I was way too aggressive with my cooling here. It's going down to over minus 200 degrees Celsius. So let's dial that back to maybe a 1000 watt. run it again. And we can run this at, save multiple results if needed. Okay, finish the simulation. So we can plot different things here. Let's go with the supply side, and we'll show some particle streams. So this is the way that the flow is going. Let's look at what happens in 100 seconds. So it's kind of circulating and eventually finding its way out through the port there. We can create a velocity a temperature contour through the Z, sure. And we can look at the local limits of this. So the outside is something like 100 degrees, 120 degrees Fahrenheit. The inside is 80 degrees. So not doing a great job of cooling our package there. So 1,000 watt is a little not quite enough. 10,000 watt is more than enough. So the real benefit is somewhere in between. And so let's crank up the temperature a little bit. I mean, crank up the cooling system a little bit, maybe double this, maybe triple it. Well, you can see how fast that this can be run. And here is, let me save this model. So we want to save this in demos, Icepak. We'll call this trailer. Okay, so now we can do a series of simulations. So this will be at 3 kilowatt of cooling. Okay, running this for 200 iterations. I can step it out for a little while, but it looks like we get to minus 16 degrees Celsius here at the minimum. There are some areas that's a little bit hotter, but it looks like we're doing a good job of freezing whatever's inside of this container at 3,000 watts. One of the nice things about Fluent and Icepak is the ability to continue the analysis to a to see what happens in transient. So now I'm going to find this door here, which is the minus Z, and I'm going to go to the cabinet, minus X, and turn this into opening. So suddenly now we've opened the door at time equals 0, but the inside is already cool to a certain extent. So let's go ahead and set up a transient simulation based on this. Did I miss it? No. So we'll keep everything the same, including radiation, but now we're going to do a transient simulation. So let's set everything to seconds. Starting time is 0. We're going to run this for 10 seconds. And you can use variable time step, initial time step. Let's have it at 100th of a second. Okay. We'll let it finish here. There's actually an interesting capability for transient simulation that wasn't in the list there, and that is this automatic transient. So here we can say initial time step. We're going to have it in 100th of a second, and minimum time step is that 100th of a second. And maximum time step is 1 second. So this way, Ansys will automatically adjust the time stepping. I'm going to save the solution every 10 steps. Ansys will adjust the time stepping depending on how well the convergence is. So it makes it easy to set up these simulations. And I'm going to say transient door open. Okay. To make use of previous results, we grab that. So we're going to interpolate the results from my steady state simulation here to my transient analysis, and that would be the starting point. So let's go ahead and run the simulation. Okay, the simulation has finished. Looks like maybe I could have used a few more steps in here, but you can see that we have from very low temperature sudden heat up of the air, and then the temperature dropping somewhat, which is interesting phenomenon. So maybe this is the initial rush of hot air, and then the cooling system kind of kicking in to once the flow stabilizes somewhat. But you can see the temperature of the actual cargo inside, at least in the center, didn't change much. Let's go ahead and say done, and we can now look at some results. So this is initial condition, suddenly opening the door. Maybe we should extend our, let's make it a bit thicker, and oh, it's not liking to extend the streamlines. Well, we can see how the hot air comes rushing in after just a few milliseconds. Okay, so this is now after about 10 seconds. And maybe smaller time steps would have been beneficial here. I also only save results every 10 steps. So those all could be results of what happened here, but we can see the temperature changing and rising up while the cool air kind of tries to fill in on the bottom here. So little transient simulation. There are a lot more things we can do with Icepak here. We can solve for individual species, in which case we can start looking at different species analysis. For example, here we have air and H2O. Now we can look at relative humidity of the inside of our trailer and look at how that changes as a function of temperature and flow. We can add dehumidifiers into the simulation. So a lot of different possibilities, but this is a quick demonstration of how you can very quickly set up a thermal simulation of something like the size of a trailer in Icepak very easily. You can easily move your equipment around, look at steady state or transient simulation, and investigate how temperature changes in the entire system. Hope you found this useful. If you have any questions, feel free to reach out to us at ozeninc.com. And if you like these videos, please subscribe and like on YouTube. Thank you and have a great day.